Hello everybody, welcome to Automotive Megatrends. I'm Martin Carl, I'm the editor of Automotive World, and I'm going to be moderating today's webinar. Today the title is Overcoming the Testing and Validation Challenges for Automated Driving. And to guide us through this topic area, I'm delighted to be joined by an expert speaker from Elektrobit, Simon Tiedemann. A little bit of background to the topic. As the complexity of automated driving functions and systems increases, so too does the cost and the complexity of testing and validation. The next hour, therefore, is dedicated to learning about the specific challenges facing automotive industry stakeholders involved in developing autonomous drive technology. Simon is Product Manager EB Assist, and today he's going to be focusing in particular on how to overcome these challenges. From the initial data gathering to the management and labeling of that data through to data processing and analysis, this webinar will outline solutions for each stage of the autonomous drive testing and validation process. As usual, we'll have a half-hour presentation followed by a half an hour or so Q&A, and we'll put as many relevant questions as possible to Simon in that time. If you'd like to ask him a question, please type it into the Q&A box, and I will try and organize those questions to get some kind of coherence in the Q&A rather than jumping backwards and forwards. And slides and a recording of the event will be made available afterwards, and we'll send you an email to let you know how and when you can access those. That's all you're going to hear from me now for the next half hour. Simon is going to talk to you about overcoming the testing and validation challenges for automated driving. Simon, the floor is yours.
Thank you, Martin, for the introduction. Hello to everybody joining this webinar. As Martin mentioned, today I will try to give you an overview about the challenges of testing and validation for autonomous driving. So my agenda for today is I will give you a short introduction about Elektrobit. We will talk about the challenges to develop driver assistance or automated driving functions. Then we will switch to the task of testing and validation of these algorithms. The next part is about our idea how this task could be solved. And then I will close the presentation. So first about Elektrobit. Elektrobit is a software product company which develops automotive-grade software for the industry for a lot of years now. We have more than 2,200 employees worldwide in 3 continents and 10 countries. We have an average growth of more than 10% per year. We're globally present in the whole world, so Austria, China, Finland, and so on. Mainly everywhere where the automotive industry is located. Since I think two and a half years now, we are wholly owned by Continental, but we are still completely independent. So for the main use cases, Continental is just another customer. We have more than 90 million vehicles running with Elektrobit software on the road and more than 1 billion embedded devices. So Elektrobit does have 4 main topics we care about. The first one is automated driving. This is where I'm belonging to. In this area, we focus on hardware and software products for development, test, visualization, and validation of driver assistance and automated driving. In addition, we have teams which take care on real functional development. So we also develop our components for serious production, so components around driver assistance and automated driving, which can run on the road. The second part is vehicle infrastructure. The main topic here is AUTOSAR standard, and embedded operating systems, single multi-core uses multi-core operating systems. Also topics like functional safety, security, and automotive networks. The next topic is the topic of connected cars. So all the ideas about big data analytics, online diagnostics, also scalable backend infrastructures. Big topic is cybersecurity, of course, and software updates over the air. And last but not least, We have teams taking care on user experience, means developing UIs for in-car infotainment systems. So we have navigation clients, we have electronic horizon provider, also tools to develop user interfaces for in-cars, and we are taking care also on augmented reality solutions. On top of that, we have consulting services, so not only for these four topics, but also for functional safety, for lean software development, agile processes, and so on. And we have a team taking care on verification and validation of embedded software. So I'm product manager for EBS's product line. A short overview of this product line. We have hardware products here, which is very special for Elektrobit, because Elektrobit mainly does have software products. But we have here also hardware products like our EBS's car box, which is a high-performance automotive-grade PC system, which you can use for testing and validation, means data logging in-car, replaying these data, simulation of these data, and so on. In addition, we have the EBS's bus tools, so these are modular I/O slot cards for high-precision data logging, replaying, and simulation, so REST-bus simulation of the common bus systems. And in addition, we have software products. EBS's Bus Mirror is directly targeting the bus tools. So this is the software support for these hardware, for testing ECU software, and well, it supports all established bus systems like Ethernet, like FlexRay CAN, and so on. In addition, we have EBS's ADTF, which is our tool for developing and testing of ADAS and AD systems. So this framework is made for data logging and for development of algorithms. We also offer a wide range of toolboxes to extend the functionality of ADTF. And the last part is the part I will focus on today, is Test Lab, which is meant as a solution for testing and validation of autonomous driving. But before I go into details on Test Lab, let me shortly talk about the challenges of developing automated driving. So with the growth of numbers of components necessary to cover the autonomous driving functionality, you have of course also an increase of complexity. But unfortunately, this is not a linear connection, but the functional complexity grows exponentially, because it doesn't scale with the number of components, but the number of interactions. In addition, if we talk about SA level 4 to 5, it's no longer possible to just hand over the control back to the driver if there is a situation you cannot cover, but at least with level 5, you have to be able to cover every kind of situation. Means especially complex traffic situations. If you ever were driving to China or India, then you know what I'm talking about. So these are very complex situations, and these have to be covered from the algorithm. Also, you have unusual situations. Means situations which you normally perhaps which appears perhaps 1 or 2 times per life. Nevertheless, these kind of situations have to be covered by a level 5 system. Same direction is hazards. So if you drive in a stormy weather, for example, this might even change the physics of your car, and you have to cover these conditions as well. And well, other difficult conditions, like as you can see on the picture, very snowy weather, so there is no chance to see lane markings. You perhaps will not see traffic signs. The cars on the side look completely different, and also these kind of conditions have to be covered by the algorithm. So what does this mean for the task of testing and validation? Well, there are a lot of theoretical numbers, and perhaps you have already heard about the 200 million kilometers without accident. We just took that number, which, well, sounds a lot, but what does it really mean? So we did some calculation, rough calculations, just to get an idea. So of course it's not possible to record 240 million kilometers for testing. So you cannot drive that. So let's say we do 5% of these test drives with real test driving, means 12 million kilometers. 12 million kilometers could be 200 cars driving around for a whole year, so 220 working days, producing more than 400 petabyte of data with an average, I think, 700 or 800 megabyte per second, what we use for calculation here. So that's one thing. You need a lot of time. You need, of course, reliable measurement, and this will create a large amount of data. Okay, but we still have 95% left. So this could be done in simulation. I mean, we do not really drive that, but it's kind of virtual test kilometers. 228 million kilometers could be split into more than 100,000 scenarios with 1 kilometer, adding 2,000 variants like different weather, stormy, sunny, rainy, different conditions, more other vehicles or other obstacles. This would lead to 185,000 days of simulation. So this is the other big challenge. We need a lot of performance, a lot of computing power to solve that. And there's one additional thing. The way of developing algorithms for the automotive industry is about to change. So in the last years, it was you have, I don't know, 5 years of development, then you have SOP, and then you're done, and then you can focus on the next topic. Well, in other software markets, you have the it's a change, like you have to go to the market with the software as early as possible, and then you have to add additional functionality over time. So this is also where update over the air comes into place, and this will dramatically change the way of how to develop automotive software. So all the update cycles must get shorter, and this creates the need to do parallel simulation and testing to accelerate testing. So what do we need to handle these kind of upcoming tasks? As I said, we need reliable measurement technology. It doesn't make sense if you want to record 12 million kilometers to stay half the time in the garage fixing something. We need suitable test environments, and we need well-matched, fully integrated solutions. So this will bring me to the idea how we think this could be solved. So this is our idea about a one-stop solution for testing and validation. Let me start from the left to right. So first of all, we need smart solutions for efficient test drives, recording, handling large amounts of data. Means you need efficient logging software. You need software which is able to record multiple sensors simultaneously with a very high bandwidth. You also need hardware which is able to support these high bandwidths and also support all the common bus types, CAN, FlexRay, LVDS, Ethernet, and so on. And because often the test drivers are not experts, you need the possibility to give an easy and direct annotation already during test drive. You need to do triggering, so trigger the recordings in important scenarios. You need recording feedback like everything is fine or the hard disk is full, or really basic level, but that this is very important for this topic of test drive recording. Next, as I said, you will not be able to record everything in real, so you need efficient solutions for generating and simulating test drive. 114,000 scenarios have to be created in my calculation. So this is nothing you can do manually or completely manually. So you need to have a possibility to make this very efficient, creating new scenarios. Also, the replay of the scenarios have to be efficient. If this is not running in real time, then it will extend the test duration. And of course, as we want to cover real test drivings, to remove real test drivings, the simulation has to be physically correct. So the ego car behavior must be physically correct. The behavior of other objects like other cars, pedestrians, and so on. And of course, the simulation of the sensors we are using have to be, well, as good as possible to replace real recordings with simulation. The next part is data enhancement. So now we have all the raw data recorded, and now we have to kind of enhance them. Means in this case, we need a high level of automation to handle all this large amount of test data. These test data have to be, for example, uploaded into a cloud by using upload facilities, disk logistics. There are different ways to get the data from the car to any kind of servers. Then you have to create some kind of basic metadata to this data. So you need to know how large this file is, how many megabytes, gigabytes this recording does have, and so on. You might even need more metadata like driving context. You could think of perhaps AI-based metadata extraction. I want to know how many traffic lights are in this scenario. Is it mainly on the highway, or is it in the city? Things like that. Then you have to label the data, means to create ground truth. This is necessary for doing test cases, and this, of course, have to be efficient. You will not be able to label 12 million kilometers completely manually. And of course, every customer is doing things like that in a different way, is interested in perhaps slightly different things. So this has to be adaptable and customizable for the customers, for the customer needs. The next part is test case management. So now we have all our data in place. We have additional information to the data. And now we want to start creating test cases. Means we have to define preconditions, like which software version to use, what is the state of the algorithm, or perhaps if we talk about hardware in the loop, what is the state of the ECU. Then we have to add a list of input data, like recordings, so real recordings, simulation scenarios, perhaps including different variations. And then we have to define the expected results. Could be ground truth, so label data, but it could also be kind of KPIs. I don't know, I don't want the algorithm to crash, or perhaps also performance KPIs like calculation duration. And well, this have to be done for the whole system, so it's probably not possible to do this all manually. So you perhaps might talk about automatic generated test cases or semi-automatic. You might want to have a history of the test cases. You want to know coverage of the test cases, and so on. So this all belongs to the test case management. The next part is test execution. So we have all the data now. We have an idea of what we want to test. Now we have to execute the test. In my opinion, it would absolutely make sense to make these transparent to the different types of testing. So it should be the same, or well, it will not be the same, but it should be as transparent as possible between HAL and SIL, so hardware in the loop, software in the loop, open loop, closed loop, and so on. This must be in a very efficient way. Means we have to support, for example, cloud solutions could be public cloud or on-premise cloud, but this will give us scalability for testing. We have to improve efficiency if we use hardware testing, things like load balancing and so on. And especially for hardware, we have to decrease downtime by, for example, automatically detect and, if possible, handle execution errors. So, for example, you can imagine that you recognize that the test duration for one of your 20 HAL systems is only a few seconds, while the others calculating for hours. Then probably something is wrong with this HAL machine. So, as a first step, you could remotely try to automatically try to restart the system, see if this solves the problem, and if this doesn't solve the problem, then you can exclude it from your HAL cluster and raise an alert for technical guy or something like that. And let me add the last topic here, test post-processing. So if we have done all the testing, we have to post-process the results. Means it doesn't really help if you have a long Excel sheet containing all the single results, but you have to create test reports. You have to administrate the test results. You have to archive the test results, probably for multiple years. You might want to compare between test results. So did the algorithm improve, for example? So these are all parts of this test execution and test post-processing. So the conclusion, to manage the test and validation of automated cars, we need comprehensive solutions. We need a flexible platform which can cover from real data to simulated data. We need automatic or semi-automatic labeling and data enhancement, so extraction of metadata. We have to manage, execute, and post-process the tests, processing, if somehow possible, in parallel. So this is where cloud computing comes into place. This would give a maximum for flexibility and scalability of the test execution. And I think we need open interfaces to also allow partners connecting to the solution to answer the needs of car makers and suppliers. So this is, we already have a lot of additional ideas in mind, so you could improve that. So that's a very long list. Let me just give you three ideas. You could, for example, improve test driving by creating metadata, so kind of annotations based on speech recognition, so the driver does not have to somehow type or press buttons or whatever, but he can just speak a comment, and then this will convert it to text and will add it to the recording. You could also talk about reducing the overall amount of test kilometers. So, well, I talked about 240 million kilometers, but is it really necessary to test all of them? Is it necessary to have hundreds and thousands of kilometers on a motorway, on a straight motorway? Or can I somehow smartly rearrange or reduce this overall amount of test kilometers without changing the result? And I think what is also important is to close the gap between recorded and simulated data. So for today, it's recorded, open loop testing, or it's simulated. You can use simulated data also for open loop testing, but it's mainly used for closed loop testing. I think we have to somehow combine that, either get from one to the other. So take real recordings and create simulations from it, or also mix it. So start with a real recording and then add simulated parts, things like that. So I think there is a lot work to do here. And this will bring me to my last topic. I don't think it makes sense that all of this is done by Elektrobit, and that's why we already started to talk to different other companies asking for partnership. We have already partnerships with simulation experts. We're talking to cloud providers, also data plugin specialists. So we're open to talk to any company which would like to support us in the task of validation for automated driving. So that was my official part, my official presentation. Thank you for listening. And well, now I'm open for questions.
Great, thank you very much. There's a lot to get our heads around there, and we've already had a number of questions come in. For those of you who haven't sent a question in yet, if you would like to ask a question, please type it into the Q&A box on the screen. Make sure it's the Q&A box, that way I get to see the questions and I can put those to Simon. We've had a question here. Could you please give us a bit more detail about how to account the test case coverage? I guess to record the test case coverage is what the questioner means.
Well, there are standard ways for calculating test case coverage, and I think this is something which really depends on the algorithm, on the specific customer. So there are standard ways to do that. So this is not really part of our solution. This is perhaps something that we could plug in here. So there are tools for calculating test coverage, but this is nothing we would develop.
Okay, and I guess tied in with that, you mentioned during the presentation about not necessarily needing to test and record miles and miles of straight road driving, when you could either simulate that or you could take just a sample from that data. Is this what you would call maybe efficiency in test drive recording?
Well, I know that I read an article, I think a year ago from a university, I don't remember the name, but they stated they are able to reduce their overall amount of test kilometers, I think to around 8 or 9,000 kilometers for the whole testing. So this is probably with a lot of additional requirements and only works for really specific tasks. But the basic idea is not that bad. So as I said, why have millions of kilometers driving on a straight on a straight highway with no other cars? There's no need to do that. You can somehow compress this, and this could be a way of reducing the overall amount of kilometers. Yeah, but I think there's a lot to do and a lot to calculate to make sure this will not change the overall result of the test.
Okay. You showed a slide that was entitled Data Enhancement, and you said that this should adapt to customer needs. You also talked about the need for partnerships in this. Can you talk a little bit about those two things, how you adapt to customer needs and how you would do that as well if you were working in partnership with somebody else?
Yeah, so we have a scene manager at Elektrobit, and this scene manager, this product contains of two parts. One is a kind of database, which allows you to search for specific scenes, like give me all the recordings which contains at least the 50% highways, things like that. But well, you need to fill that database with information, and for this we have a tool, an analyzing tool, which analyzes all the recorded data. And this tool is not static, but it's designed as a kind of framework, and you're able to add your own plugins into that tool. Means you can take your own algorithms for detecting, I don't know, counting the number of traffic lights, and then write that information to the database. So this is something also the customers can do.
Okay, we talked about not needing to do all of the road drive testing because some of it will be repetitive or not necessarily useful data. We've had a question about how much of that can be synthetic rather than real-life recorded data. So how safe is it to scale up some of that data in order to complete those gaps versus doing that driving, really actually doing those miles?
Well, in interesting situations, and I had a lot of discussions about that because, well, if you simulate, it's probably close to reality, but it's not reality. So I think it's not possible to have, for example, 100% simulation. There are ideas, a lot of calculations. So one idea, for example, could be that I do not really test my algorithm based on real data, but I start to test my simulation based on real data. So I have a small set, so small, only a few thousand kilometers perhaps, which I have in real recording, and I have the same in virtual. And then I run algorithms on that, and I compare the results. And then there are probably stochastical ways to find out if the simulation is, let's say, acceptable. So it's as close to the reality as we need it, and then you can use the simulation to test your algorithm. So this is one idea. I don't think there is right now a real number like what I stated: 5% real, 95% simulated. So that was just an example calculation. I don't think there is a final number yet. A lot of theory at the moment, but well, nobody have tested it practically right now.
How, I mean, this may be beyond the realms of the areas in which you work, but how do you decide what is a real-life test scenario? We hear that Singapore, for example, is leading the way when it comes to autonomous vehicle testing, and they've got cars on the road in real-life situations. But they also have very well-ordered roads with very clear road marking. Everybody obeys the rules on the roads there, and it's a very sort of scientific and lab-like environment in which to test those vehicles versus somewhere like Michigan or even parts of the UK where the road conditions are very poor. There's very poor maintenance of hedges, for example, in the UK, and hedgerows. Lighting's not very good. Road markings aren't very clear. So how do you decide when the vehicle's being tested, whether this is this in itself, even if it's real life, is this true to other real life situations?
Well, if it's a real life situation you have recorded, then it's a valid test case. Nevertheless, the main question probably is, do I have all relevant test cases? And that's a very, very hard question. So, well, there are a lot of articles and you can find a lot of stories in the internet, for example. One big topic here is artificial intelligence, so learning-based algorithms. And there are so many examples how this went wrong because you selected the wrong set of recordings to train the algorithm. So that's very hard to answer, how to be sure that that you have everything you need to have, well, to cover all in any kind of possible situation. Probably this is, you cannot be 100% sure here. It's yeah, you have to get as close as possible, but you will probably never reach 100%.
Okay. And on this basis of simulation testing, do you envisage consumers, or is there any kind of public relations aspect to telling consumers that their cars have been tested in real life as opposed to via simulation? So if a consumer were to know that a car had only been tested out in the field, they would have a different reaction to if they knew that a large proportion, not necessarily majority, but a proportion of the testing had been done via simulation. And I appreciate entirely that other parts of vehicle testing is done via simulation, but I guess it's this sort of mental hurdle that we have to overcome, that this is associated with an autonomous vehicle as opposed to a manually driven car.
Well, I think the acceptance of self-driving car itself is something we have to face, and this is probably nothing which you can somehow teach. This is more probably perhaps a generation question. So a lot of people which nowadays drive with cars will never accept self-driving cars. I don't know if this is really a question of telling the people how many kilometers we were really driving and how many kilometers we have simulated. Perhaps I'm wrong, but I don't think. Well, do you ask nowadays how the cars nowadays are, of course, tested as well, but nobody really, the consumer does not really ask how this testing is done. So he just have a kind of trust to the OEM that the OEM is doing the best he can to test the car, and whatever he thinks is necessary to do that. And I think it will be the same for this question. So I don't think the customer is really interested in the percentage between real drivings and simulation. He just want to be sure, well, that it works. And this is mainly well, if you follow the press about like accidents with Tesla self-driving cars. So I think this is the level where the consumers are talking and thinking, and nobody asks Tesla how they test in detail. They just recognize if it works or not.
Okay, interesting. We've had a question here about somebody asking about a comment that you made during the presentation. I think you said that there will be 2,000 variants just of one scenario. Which parameters do you plan to vary?
Okay, so this is nothing we have today. It's just a theoretical number. You can, of course, double the number of scenarios and make the number of variants half. I just want to state that it's a very, very large number. So don't name it down on the 2,000 variants. Well, I think it's not only 2 or 3 variants like rain and sun and fog and snow, but you could also add 1, 2, 3, 4, 10, 100 other vehicles. You can change the behavior of the of the road. You can make perhaps one sensor fail. You can add pedestrians. You can change the time. So every hour does have other lightnings, for example, day, night, noon, evening, and so on. So there are ways to create lots of variants in this simulation. I don't know if 2000 is a number you can really achieve. All I want to was the intention of this slide was to give you an idea how much this is. That's a very huge number we need here.
Okay, interesting. During your answer there, you mentioned making a sensor fail, and that ties in nicely with another question we've had, which reads as follows. Sensor performance is obviously a key factor for autonomous driving. Can you please briefly outline how sensor performance is addressed for a simulated autonomous driving scenario?
Well, that's more a question for the functional development. So they, of course, rely on well, good sensors. Let's say like that. So the main question is, what is good? Unfortunately, that's nothing I can answer. So we have colleagues here. They are focusing on functional development. They do things like sensor data fusion and stuff like that, and they can probably tell a lot about the quality of sensors which is necessary. So that's unfortunately nothing I can answer.
Okay. Somebody's put in. We've had several questions about cost here, and I'm going to guess right now that you don't want to talk about cost, but we could perhaps talk about the level of work that's involved. So the question here is, how much does it cost to do all this labeling of video cases, cost per kilometer, cost per frame, and how much of the labeling can be automated? If you can refer to cost at all, that'd be very useful, but perhaps you can describe how the process is carried out and what sort of level of effort is required in doing all of this.
You mean the effort for the
labeling of video cases?
So for the customer to do labeling, or what do you mean? Or the cost for us to create this kind of
for you,
label tools? Well, especially in the kind of in the area of data labeling, we're at the moment talking to different partners. So this is one topic which we probably would like to cover with partners. So I'm not an expert on labeling here, but I know that this kind of tools do have algorithms included which improves the labeling. So, for example, you could, if we talk about labeling, we mainly talk about video labeling, so marking objects in a video. What you could do to improve this labeling is that you mark an object once in one image, and then this is tracked through the scene, and you just have to check if the tracking works. But there are other ways which to create ground truth with where you don't need a label tool, but you can, for example, add a test add a reference sensor, so a very high precision sensor to a test vehicle, and do test drive with that, and then add algorithms, perhaps very complex algorithms, which need a lot of computing powers to automatically generate labels. Nevertheless, they're created automatically, so you have to somehow verify them. So there are, I don't know, dozens of ways to create ground truth data, and so there is not that single number how much effort it is. It depends on what type of ground truth you want to have, what yeah, what accuracy you expect and so on. I know these label tools, so we are talking, as I said, to partners, and some of these label tools also allow to add your own plugins to do this kind of automatic labeling. So this is again possible for the customer to improve the tool itself.
Okay. I'm interested to know, when the testing is carried out, how much data is recorded. Do you record the driving data, or do you also record things like how much power is consumed at certain times during certain events? More power is being consumed by the vehicle, and whether that's something that can be monitored, controlled, and reduced.
Well,
or is that an aspect that's not part of this testing?
What you record is, well, I was talking to a guy which is responsible for the driver assistance and automated driving test recording with a big OEM, and he told me the most expensive data is the data you do not record, because there will be a time and then you will recognize that you need that information. So the main idea is to record everything which is on the car bus. Means all the data from the sensors, all the communication between the ECUs. If possible, just record everything. And if power consumption is available as a signal on a CAN bus or on a FlexRay bus, then you just record it. Nevertheless, well, this creates a huge amount of data. So I know nowadays we talk about 700-800 megabytes per second. Driving around 1 year and record 700 megabytes per second creates, yeah, as I said, hundreds of petabytes. So you could improve your test driving. For example, you could data or the data streams with low bandwidth like CAN or FlexRay, you can record them all the time, and whenever something interesting happens, you could add the video stream to the recording. But well, as I said, this creates the risk that you perhaps at a later time are interested in something which you were not aware during the recording, and then you don't have the data and you have to drive around again.
Okay, we did have a couple of questions actually about the capturing of events. One in particular asked, and this ties into your answer just there, can you explain in more detail how you manually and or automatically annotate testing data in real time? How do you capture events perhaps not directly observed by the operator?
Well, as I said, operator is one source for this kind of triggers, but you could also, well, you have all the communication of the cars, all the sensor data available in your logging system. And for example, for ADTF, we created algorithms which allow to specify kind of trigger rules. So, for example, if the speed of the car is higher than 50 kilometers per hour and the driver presses the brake with at least 50% of maximum power, then I want to trigger recording. And for example, in ADTF, but also for other recording solutions, it's often possible that you do not start recording at this time when this event happens, but you can add kind of history, or you have buffers. So the last 10 seconds of all those streams is buffered, and then you can store this information. So the last 10 seconds plus the next, I don't know, 60 seconds, you can store that in a file.
Okay, you mentioned cybersecurity during your the early part of your presentation, and somebody has sent in a question. I wonder if this is relevant to sort of some of the extremes on cybersecurity. Do any of your simulation scenarios reflect what could happen in the event of a particular cyber attack that hits whilst driving?
That's a good question. So we have the subsidiary called Argus, which are focusing on the topic cybersecurity. I was not yet in touch with them, but I like their idea. I think you should at least think about stuff like that. So what you for sure have to test is errors in your sensors, like malfunction of your sensors and stuff like that. And well, if I think about it, a intrusion, so a hacker attack to the car, well, you could take this as malfunction of the system. So I haven't thought about that, to be honest, but it's not a bad idea. I think you should also test things like that, because well, you probably you will not get 100% secure system. I think that's impossible. So you should at least spend a few hours thinking about how to cover these kind of attacks.
Interesting. And I wonder if, rather than talking about the sort of attacks that might never happen, but we need to be prepared for, more random scenarios are things like children running out between cars, something which is very difficult to test for, because obviously that's a situation that if it happens during testing, the car needs to be stopped very, very quickly, but it's not something that can easily be programmed in. So how do you accommodate this kind of situation where it's something that you don't want to happen, but at the same time it needs to be, the car needs to know how to react? We know that a human would react in a certain way already. So
that's exactly one of these situations, of these unusual situations. You are not able to record them because they just not happened while you're driving, or you just don't want to record them, like, I don't know, any kind of crash. Well, you could of course make a crash, but you don't want to do that, of course. So these are exactly these kind of situations where you have to use simulation. And then again, it's the question. So if this child running on the street, if this scenario is only tested with simulation, how can we make sure that it behaves the same if we have real data? That's something you have to focus on. As I said, one idea is to validate the simulation with real data. Another way could be to mix reality and simulation. So let's say we have a real recording of an empty road, and then we simulate a child. So it's still not 100%, but we get closer to the reality by mixing real data and simulated data. And this is, I think, the way how to cover these kind of situations.
And similarly, less extreme and much more feasible for testing is taking a car through, let's say, some roadworks where the traffic markings have been disrupted. Maybe there's contraflow in place, temporary traffic lights that may not be working, that kind of thing. Is that the sort of edge case scenarios that you would still put these vehicles through?
Well, yes, of course. Having traffic lights which do not work, or heavy, I don't know, slippy roads or something like that. This is something you can record. I think this is also an important task for guys like test recording managers, so people who think about how many kilometers of which scenario do I need. You need to know how many data do I have already. Is there a gap to what I need? Do I have to send out my test drivers to exactly search for these kind of scenarios? Nevertheless, this is something you can drive. So you can have real data, and of course, again, you can extend this with simulated data. Also, another way of of getting recordings with this kind of situations is already done nowadays for driver assistance algorithms like emergency brake. So to test if the emergency brake system works correctly, you don't want to drive into another car, into another real car, but you can, for example, place dummies on the road and test like that.
Okay, we know that simulation software is becoming more and more accurate, much more reliable than it ever has been, and it's being used in increasing aspects of vehicle manufacturing and design process. How have you tested the accuracy of the simulations, and how close or accurate have these simulations been?
I have not yet tested the accuracy of simulations. I think that's a very big task. So this will not work with a few kilometers to be sure that the simulation is accurate. As I said, we are in contact. We are partnering with simulation experts, and this will for sure be a topic for the next years. I'm not yet sure if this is a task we will do, or if this is something our partners will do, or perhaps we do this together. So it's not yet done, but I think it's absolutely necessary if we want to rely on simulation as input for testing.
Okay. We've had an interesting question about maps, and I wonder if you can take this question on. When we move to map-based autonomous driving, how and where can we include map validation in test setup?
Well, from a high level view, map is, well, it's mainly just another type of sensor. It's different to the common sensors. So it's different to radar, to lidar, to a camera. But you can probably treat that from the testing perspective. You can treat that like other sensors, and then we talk about the quality of sensors. And well, that's nothing we at EBSIS are focusing on. So this is a question for the function developers. Do they have sensors which have the quality they need for their algorithms? For the testing purpose, it's just you simulate the quality of the sensor. So you simulate I don't know, the number of pixels of your camera. So you can adapt your simulation. Of course, you have to make sure that your real recordings match to the final solution, to the final car. And then you just test it, and then you get a result. And the result could be it doesn't work, and you have to get more expensive sensors. But well, the decision if the quality of the sensor is good enough is not a question for the validation, for the testing, but that's a question the developers of the functional algorithm have to think about.
On the topic of the quality of the sensors, if the sensors being used during the testing process are deemed to be not as good quality as the next generation that comes along, then presumably all of that testing has to be done again, or is there a way of testing just the incremental difference?
Well, that's well, I think reuse of data is a very important question, but I fear it's not that easy. So you cannot. Well, if you talk about real data, if you change the sensor, then you might have a problem because you cannot, at least you cannot test the whole system with the old data because it does not match the features of the new sensor. You could test parts of your AD system. So, for example, the common idea of an autonomous driving architecture is that you have several levels. You have, well, the easiest split is sense, plan, act. The sense part is the one which really belongs to, which really relies on the sensors. Plan and act, you could test this. This is not that much depending on the sensors. So there is a kind of abstraction, and you could perhaps partly reuse real data, but I think the better way is to use the real data to make sure simulation works, and perhaps to create scenarios in simulation, and then test based on simulation. Because if you have a simulated environment, you can easily change the sensor. You can just increase the number of pixels of your camera, and then simulate it again, and then you're done.
That's a perfect moment to wrap up. I'm going to draw this session to a close. Thank you very much, Simon, for sharing your insight with us. Thank you to Elektrobit for making today possible. And thank you, of course, to everybody who joined us and sent in questions. There was a great interest in this, and I'm sure that you're going to be hearing much more from the people who joined this webinar. We will be sending a link out to everybody who joined us today to let you know how and when you can access the slides, as well as a recording of the webinar, which you can watch on demand. And with that, I'd like to thank everybody, and we'll see you at the next webinar. Thanks very much, and goodbye.